coming.
Oh, okay.
Yes. Well, it's still okay. Compared to US, it's better.
It's better actually. You're not sure what it happens.
Here is 7 hours, but somehow, I mean, especially for conference, I think to Europe is easier because I fly in this direction. At least I like it. The jet lag is lighter. Yeah. So when I go back, well, anyway, I don't care.
Yeah. The first actually is to the United States.
No, the 2 years is always the hardest.
Yeah, but you find your way.
No. It's somehow.
Oh, it depends where you.
Somehow, I think it's. But then I would not be able to get up in the morning.
Oh, okay, yeah.
It's hard.
No, I was wondering if you from Korea, which direction you fly.
Go to Europe, just that's the other direction.
Yeah, so that's the harder direction.
Yeah.
Yeah, that's what I meant. Careful. Can you check the session maybe? Neither do I. Yeah, I saw your message. I haven't printed it yet, but I'll just.
For some reason I cannot print it.
Okay.
Some IP address conflict.
Okay, well, yeah, I'll do it.
I was here yesterday. We went for another conference over the weekend.
Oh, you went to that one too. The kitchen they're excellent. Indian stuff.
So if you're really big wedding in here or in India? I need all the details because we were talking about this last year. When was the bunch thing? 2 years ago? 1 year ago? I don't remember what was the storyline at the time. We were totally objecting to the idea of marrying.
Oh, that's it.
So you're starting this with you're showing me 2 hour wedding? So you did a really big thing then. Yeah. So small, still it was 200 people, I guess.
Okay, so let's start the afternoon session. Machine 1, we're going to talk about the field interferometry at 5.5 into velocity.
Thank you. Okay, so first I'd like to thank the organizer for inviting me here. This is my first time to Stockholm. Very nice city. I want to talk about the neutral velocity and decoherence in the conformal interferometer, but I understand last week Kirill Schlenker gave a talk on interferometer. So I'd probably spend more time on the introduction part where I want to talk about these microscopic calculations done on a disk where we can treat edge modes, especially we can get the energetics, that is the velocities from these microscopic calculations. So for the record, my name is pronounced as Xin, X-I-N, Xin. And I'm from the APCDP. I just want to mention here's the list of my collaborators basically on this project on calculating quantum Hall systems on a disk. So as I move from US to Europe and back to Asia, so you see the list expand. And since I was educated in an engineering department, I would like to especially thank Professor Deng Sui and his former student and postdocs, from whom I learned a lot of the experimental issues, and you will certainly find the marks in the research that I've been doing. So the motivation, of course, is now the interference experiment is believed to be the most crucial one that one actually finds the signature of nonlinear statistics. So we want to understand this experiment, and Bob Willett has done some nice experiment on it. And using microscopic numerical calculations, we can actually get some realistic estimate of the velocity, therefore the coherent length and temperature. And I'd like to discuss a little bit about from these microscopic calculations, the ability of how to enhance the signature of nonlinear statistics. So here's the outline of my talk. I'd like to first discuss the edge excitations and the edge mode velocities. And as I said, I would then talk about 5-half, but this probably would be a little bit shortened. So by now, I guess you don't need any introduction to fractional Cohen-Hall effect. And Bert Halperin, back in 1982, first pointed out the importance of understanding fractional Cohen-Hall effects through the edge, because although the system has bulk gap, it nevertheless supports chiral and gapless edge excitations, and these are crucial to the understanding of the current flow in the system. So for the Laughlin states, there's no back scattering. The edge mode is chiral, and we have chiral Fermi liquid. Well, in the original case, the integer case, we have chiral Fermi liquid. So we can construct these edge theory by in the non-interacting case by explicitly writing down the density operator as the product of creation and annihilation operators, as was done by Haldane, for example. And we can introduce a bosonic field phi, which is related to the density of the edge wave, and this density, this phi and the electron operator, which is basically a vertex operator of phi, and satisfies certain propagator relation that is just that will give rise to the normal ohmic law. And in this construction, one can see that the edge mode velocity is nothing but the Fermi velocity. But suppose now we move on to the interacting case. We no longer can construct the edge theory using creation and annihilation operators. As Xiaogang Wen pointed out, that somehow these density operators are still well defined, then they generate the low energy excited states. Here the density operators satisfy certain algebra known as Kac-Midi algebra. And the physics of these density density operator is really just the deformation of the edge of the droplet, because we have an incompressible liquid. So everything seems to be the same, except we've seen these anomalous exponent gets picked up. So we end up with, if we somehow measure the edge tunneling current, we measure the non-ohmic law, and this is the chiral-Rodinger liquid behavior. So how do we test the idea of chiral-Rodinger liquid theory? One can actually put the Cohen-Hall liquid on a disk. So this is taken out from Xiaogang Wen's paper, and so he basically used a V1 potential in a, language of Haldane pseudopotential. So if one diagonalize the Hamiltonian, one finds that a series of zero energy ground state, and the one with the smallest angular momentum is the Laplace state, because it has the smallest angular momentum, so it cannot be compressed, so it is incompressible. Beyond this ground state at higher angular momentum, we also have these zero energy states, and these are the edge states. If one counts the number of the zero energy states here, one get 1, 2, 3, 5, 7, 11. And these numbers are generated basically by this generation function in agreement with the Bordonic edge theory. So of course, if you use a V1 potential, then we have all the edge modes at zero energy, which says that the edge velocity is zero. But this, as you know, is not the real situation. So in reality, we want to look at a model that, to the best of our capability, model the real experimental situation. So we consider here an electron layer, and this one is not another electron layer. This actually is the background charge layer. The reason that I put the background charge on top of the electron layer with a distance d is because with real sample considerations, we normally have two-dimensional electron gas at this gallium arsenide, gallium aluminum arsenide quantum well or heterostructure. But in order to enhance the mobility of the two-dimensional electron system, normally the impurities are doped away from the two-dimensional electron layer. They're somewhere above, I think, somewhere here. These are the silicon doping. This is known as the modulation doping. So for experimental consideration, we want to put the charge somewhere above the two-dimensional electron layer. And another reason is that by tuning this distance, we are able to tune the strength of the confining potential that the electron feels in this electron layer. And so the Hamiltonian of our system would contain basically Coulomb interaction and the confining potential, and we want to study the competition between these two terms. Two important ingredients here is one is the charge neutrality, as I just mentioned, which is which provides a realistic confining potential, and also which actually gets rid of some divergence in Coulomb interaction. The other ingredient is ground stability. I picked the name actually from one of Claudio Chaman's paper. I used to call it something else, but I like the word, so I just picked it. And this says that a realistic wave function. Well, as you know, we can write down all kinds of trial wave function for quantum Hall state, but which of the wave function can be real or which of the wave function may not be real? In my approach, I want to put it into numerical models, and if this wave function can be the global ground state of certain in certain parameter space, then I call this wave function ground state. So as an example, I started 1/3 Laughlin case. I put 6 electrons within like 18 orbitals. As I tune the d, the distance between the background charge and the electron layer, from 0.1 magnetic length all the way up to 5 magnetic lengths. This is the energy spectrum as a function of total angular momentum. So as you can see, for small d, these ground state angular momentum is fixed at 45, and this is the momentum for the laughing state. But when d increases beyond certain value, and the ground state becomes different, and that's why I write down here the laughing state is ground stateable below this dc of 1.5 plus minus 0.1. The physics here is related to edge reconstruction. I will talk about later. So just to show you how the wave function looks like this is for 9 electron and 3 more. So below the edge reconstruction threshold, this is the density profile of this ground state, and this blue lines here is the density profile of a laughing state, and you can see that they agree with each other fairly well with some 95% overlap.
Sorry, on your previous slide you said that the experimental value of the separation was 8 to 10
Yes.
millivolts, so do you know why the discrepancy happens between?
Okay, so the we sort of understand as the distance increases, there will be edge reconstruction. Basically, there will be some edge droplet separating from the electron droplet. But as you separate, the effective potential left for the inner droplet changes. So the situation actually forced after this d, the situation forced back to the strong confinement situation. Then you can further increase d. So you basically end up with multiple, I think, these edge puddles. And still in the bulk you have this laughing state, for example. As you'll see, I will give you more data. So after edge reconstruction, you see these density modulations, and which gives you a hint that this edge puddle here may separate from the bulk when this d further increases. But again, this is very small system. I cannot show you. Of course, we have data that suggests the separation of the two, but the number of electron left here is very small, so you don't really necessarily call that a bulk. So apart from the laughing state being ground state in this setup, I can also create quasi-particles, both quasi-Hall and quasi-particles actually, using some trapping potential at the center. Here specifically I use a Gaussian trap, and for somewhere here I can use a positive, a negative potential, I think, to repel the electron from the center, so creating a hole in the middle. If you count the charge difference between this one and the laughing state, then you get roughly 1/3. So this is 1/3 quasi-Hall excitation. And if I do it with positive potential, then I detract the electron at the center, so to form a quasi-particle. So basically, I can use this Gaussian potential to tune continuously between quasi-Hall state to laughing state and to quasi-particle state. They are all ground state of my Hamiltonian in the corresponding parameter space. So, of course, the reason we use the disk geometry is that we want to study edge excitations. As you know, edge excitations are generated by Kac-Moody algebra, or using wave functions. These are the symmetric polynomials multiplied by the Laughlin states, and the symmetric polynomial space is spanned by this kind of form, and so one can easily get the countings correct. And so basically you can see here I have ground state, then 1, 1, 2, 3, 5. Compared to the one that I showed you earlier with the V1 potential, I here get some energy scales, and I'll show you in the next slides that they satisfy this energy and momentum summation rules. So one can easily identify these states, although here you already see mixture between the edge states and the bulk states. So one can actually, if one is able to identify these modes, then one can get the charge velocity correctly from this identification. So, for example, this is the only edge, the lowest energy mode in the delta m equals 1, which means the angular momentum is just 1 greater than the Laughlin state. So you see, this is the excitation, but you can see also this arrow here can be moved around, and you see these energy differences are exactly the same as these two. These are so suggesting that this one is a good edge mode. And now we also, it's not showing up right anyway. So now we know we know the origin of these modes, but we don't know this one. So this one actually is a delta m equals 2 excitations. It's not shown here, but it is also, the energy difference is the same as this to this and this to that. So that's the delta m equals 3 mode. And as you can see, this mode can either be interpreted as a delta m equals 3 excitation followed by a delta m equals 1 excitation, or delta m equals 1 followed by delta m equals 3. So there are these triangular rules. And we're left with this guy here. So this analysis tells us that we are able to separate these edge modes into one boson edge excitations and multiple boson excitations. And this one here is the edge mode dispersion we want to get. So from this delta U versus delta M, we have two ways of getting an estimate of the velocity. One through the difference of the lowest two mode, and the other through the derivative of this curve near delta M equals 0. And here I showed the finite size scaling of these two definitions. As you can see, in the thermodynamic limit, they seem to agree, although at finite system, the definition of difference seems to be better. So I will, in the later discussion, use the difference between the ground state and the lowest edge excitation mode to define the charge velocity.
Sorry, so the lowest excitation mode is special because that's just translation, is that right?
Exactly, yeah.
So, is that really a kosher thing to do? I would think that one should ignore that one and look at the second or something.
In the end, it's pretty much the same.
Yeah. Okay, another question. So what you have is a non-interacting Bose spectrum.
Yes.
Did you look at what the corrections to non-interacting are? I mean, it's such a small system, you would actually expect there to be strong corrections, but in fact,
Yeah, there is some. It's a bit slow, but okay. So yeah. So for this mode, for example, there are some discrepancy, but still small for some reason. I think you can already see some discrepancy here. So now we put everything together at different fillings. This is the valence filling fraction. So basically for 5/2 we put it at 1/2. And some of the modes I will talk about later. So one thing we notice that is these are the charge modes. They have a range because the edge mode velocity in general depends on interaction and the confining potential. Here I'm talking about the dependence on confining potential. So you do see a range, and the bigger the range is, the more stable this corresponding ground state is. As you can see, the 1/3 state is probably the most stable one, but 2/5 state is not that stable. So the charge velocities can roughly be fit by this law. It's just the energy scale multiplied by this valence filling fraction. And this is the neutral mode. For 5/2, you see this huge difference between the charge and the neutral one. This one here is presumably the neutral mode for 2/3, although many people expect this mode velocity should be small. In numerical calculation, we found that it is not so. So we want to compare this result a little bit with the experimental measurement. In recent experiments, people found this charge velocity to be in the range of 10⁶ centimeters per second, and 4 times 10 to the 4 for nu equals 1, and 4 times 10⁶ for nu equals 1/3. Here I plotted this number for gallium arsenide. As you can see, roughly we get the numbers correct.
So numerically, how do you tell that something is a charge versus neutral, just by looking at the numerics?
Okay, I guess the issue is just these two. As I move on, I will talk about
So right
these
now,
things.
it's just that you have...
Okay, for this one probably it's easier because it's non-chiral, so charge mode move in one direction and neutral one in the other direction. And for this one, the charge and neutral one, they are very different. One is bosonic, the other is fermionic, so they have very different spectrum, which we can also use to identify them.
And experimentally, can they look at the neutral mode at all? Do they have
In the next one, I probably will show you the. Actually, it's no. So far, we haven't calculated that. So I just want to say a few things on the previous plot. That we actually see this limited range of velocity. This has something to do with my model, and I believe it might as well in real system. So charge neutrality actually guarantees the edge potential being smooth, so there's no singularity. This limits the edge mode velocity from above. And then you ask a question, why in weaker and weaker confinement these edge mode velocities does not drop to 0? As I mentioned a little bit, the reason is due to the edge instability. By generating these edge density puddles, the quantum Hall droplet can generate stronger confining potential to stabilize these the incompressible liquid, and therefore stabilize the edge modes. So the edge reconstruction basically generates additional edge modes propagating in opposite directions, and you know that they must be coupled by Coulomb interaction or impurities. So in the end, one should get one charge mode and several neutral modes. So now we encountered a few situations where we can have neutral modes. Because these neutral modes, we don't have good understanding, so I just list them together. So one is in the non-chiral control state, like 2/3. Second is in edge reconstruction, as I discussed here, and the third one is from non-abelian control states. It looks like we have the best understanding actually in this non-abelian case. So, as I said, there's no success in detecting neutral modes in experiment. So, for example, at the 2/3 filling, this can be as proposed by McDonald and one that the 2/3 droplet can be understood as a nu equals 1 electron droplet, subtracting or adding a nu equals 1/3 whole droplet. So it looks like something like this. So we have 2 edges and 1 edge mode for each. Numerically, we can do this case and we can identify the edge excitations in both directions. So this is a non-chiral case, remember. So we have these charge modes here. The energy scale that I showed earlier agree with the other charge modes, which is proportional to the filling fraction. And we also have setup modes, edge excitations here, and these are what I call neutral mode, because the one in the right direction is consistent with the charge one, then this naturally should be thought of as the neutral ones. But experimentally, some group attempt to look for this neutral mode. They found no evidence. For example, in Post-Thomas group, they set up a geometry like this, where they have 2 contacts. They can send some electron pulse in, then measure the response at the other contact. They can do it asymmetrically, but then they can switch the direction of the magnetic field or switch the direction of the source and drain. So this 2-way they measure these are the 2 set of signals they measured, and you hardly see any difference except for the delay because of the difference in the path in these 2 directions. So this experiment told us nothing about the existence of the neutral mode. There are recent proposals of detecting neutral modes either from thermal measurement, which is hard, and momentum resolved measurement, which is I think Matt Grayson actually tried with this special geometry, but also he didn't publish anything. And there's also one recent proposal by Claudio Schaman using a line junction to do the measurement. So we will look forward to see whether experimentalists will tell us the existence of the neutral mode. So the edge reconstruction I promised to talk about. So this was proposed in the context of the integer quantum Hall effect by again McDonald's group and Chavarin's group. And the basic idea is in the strong confining potential, the density droplet looks like like this. So there's 1 electron droplet. But in weaker and weaker confining potential, it is possible to separate a puddle of electron out. So in the density profile, it looks like a separate edge droplet. So in this case, now we have counter-propagating edge modes like this. So by coupling these modes using Coulomb interaction, it is possible to have 1 charge mode and additional neutral modes. So that was the idea of edge reconstruction. Schaman and Wan actually gave some numerical evidence for that. They showed that by tuning the edge confining potential through the background charge density, they can, they show these change of ground state angular momentum, which they, and also the density profile of the the droplet. And they use these to support the idea of edge reconstruction in the integer case. And I just want to point out that this actually is quite easy to understand on the electrostatic level. It's because, at least in the model that I'm considering, so this is the background confining, this is the background charge, and that's the electron charge. And you can view this system as a parallel capacitor. And if you calculate the energy for moving an electron near the edge to the edge, then you will find this energy scale increases as this d increase. So this creates the natural tendency for the electron to move out to form a separate edge droplet. Of course, one can actually develop this phenomenological field theory approach. Show that the edge dispersion is possible to develop certain Rotan minimum-like structure, and if the density, if the confining potential is weak enough, and this may create additional condensate near some finite momentum, and in the end we have non-chiral edge excitations. So we found some numerical support for this picture, and remember this is this lowest energy mode in each momentum sector is the bosonic edge mode, and you see this Rotan minimum developing, and at a certain stage near d equals 1.5, you see the condensation of the Rotan mode, and which can be can be even lower. So one interesting thing is to ask, okay, so as proposed by the Chavin one, that after edge reconstruction we'll get a set of charge mode and multiple neutral modes. Do we really have some evidence for the existence of such separation? So one can look at such quantity, basically is the tunneling spectral function. One start from n electron Laughing state, then add an electron at with certain momentum, then one measures the overlap with the n+1 electron with certain edge excitations. So by doing, we can compare these numbers with the Karl-Lottinger liquid theory. So one finds that with reconstruction, there's one branch of modes which roughly agrees with the Karl-Lottinger liquid theory, suggesting that we do have a set of edge, the charge mode after the edge reconstruction, and you can compare this with the edge states before reconstruction. They look very similar. So these are the numerical results. So for instance, the lowest mode, the Karl-Lottinger liquid predict that we should get something like 3, and before the edge reconstruction we get 2.8. After edge reconstruction we get 2.845, and you can look at all these modes and understand that such identification is very, very good. So this is some microscopic evidence for the existence of charge modes as the result of mode coupling. So whether this has anything to do with the edge tunneling measurement is still a difficult question, although we addressed this issue in one of the papers. I'm not going to elaborate on this. So I will now switch gear to talk about the 5-half state, which I assume these days people are more interested. Before I move on, are there any questions regarding the first part? Yeah.
Do you have any comments on the previous slide on this deviation from
This one.
yeah.
Well, so this part is hard because we have 3 or 4 set of 3 or 4 experiments from different groups, but they are more or less all related to Dan. And the original one says, well, at 1/3 the exponent is in good agreement with the Chiral-Lagrange liquid theory. But the second one says, okay, at 1/3 it is still so. But according to the Chiral-Lagrange liquid theory, there should be additional states, like the Jane sequence should be, they should have the same exponent here. So it's a plateau. But Matt Grayson's experiment showed a continuous curve which can roughly be fit by alpha equals 1/μ. And my Thiorkis data also suggests that, well, this is a function of 1/μ, but they seem to be different. So 1/μ is really something related to charge, because μ is filling fraction, so it's charge. So this, as far as I understand, this roughly says, that in the tunneling measurement you detect the charge mode. But the detail of the exponent may depend on the sample, as a lot of Darcy have proposed.
So that is what is believed now. It's the edge. It is the sample that gives this delay.
It's probably is, but if you ask the others, they might have their things to do. Okay, so we're interested in the 5/2 state. I just want to make a short comment on the 2 plus 2/5 state. I also tried this, very hard to look for some evidence for visualized state, but I seem to get a ground state with different angular momentums, but none of that fits the Reed result description. Although I do get the hierarchical state in the lowest Landau level, not the first excited Landau level. Okay, so this even denominated Cohen-Moore effect is very exotic, as you can see, most of the fraction Cohen-Moore states that we know today are odd denominators. But 5/2 state really is a good fraction Cohen-Moore state, as one can show in these RXX, the minimum of the longitudinal resistivity versus temperature plot. You see this activated behavior as on the semi-log plot. So from which one can extract the gap of the fraction component. So the laughing state or fractional component state for at 1/3 or 1/5, and maybe the hierarchical state can be understood as the condensate of composite bosons, or alternatively as the integral component effect for composite fermions. But at filling fraction 1/2, if you use the same argument, then we have composite fermia at 0 effective magnetic field. So one might expect that we can have a situation where we have Fermi seas of composite fermions. This seems to be the case in the lowest Landau level. Or we can have paired composite fermia, and this is happening. At least seriously believe it is happening at the first excited Landau level. And at even higher Landau levels, we might see these charge density wave. So anisotropic transport behavior. And of course, the Moreet Pfeffian wave functions served as the starting point to understand the 5/2 state, which in the most simple language probably is understood as the BCS wave function with weak complex P wave pairing. P minus IP. and one can project this BCS wave function into real space and get the Pfaffian wave function. And for a legitimate wave function, we need to add these the charge part of it. This complex P-wave paired state supports a half-flux quantum vortex in which a zero-modal Majorana fermion lives. So this corresponds to the charge E/4 quasi-Hall in fractional quantum Hall state. But as I said here, the Moore-Reid wave function not only contains this pairing wave function, it also contains the charge part. So it is reflected in this quasi-Hall operator. It contains these neutral fermionic part and also the bosonic part. So now one can also put these two E/4 quasi-Hall or quasi-particles together to get an E/2 quasi-Hall or quasi-particle. And in one case, one get only the bosonic component, and the other case will get both bosonic and the fermionic. So if you look at the scaling dimension, this one is irrelevant, to inter-edge tunneling in RG sense. But this E/2 quasi-Hall is also relevant, but it is less relevant than the E/4 quasi-particle. Okay, I just like to point this out, and as one see both contribution of both in the real experimental data. So how do quasi-Hall look like in the Moore-Reid case? We did the same trick, and using a trapping potential in the center, we can create a E/4 quasi-Hall, which is smaller dip at the center, or an E/2 quasi-Hall, which is a deeper dip at the center. I think we can only get one E/2 quasi-Hall state because there's a global constraint on the wave function, so we do not have the fermion sector. So if you're not happy with the small system calculation, this one is from quantum Monte Carlo calculation, and you can roughly see there's a dip at the center. This is E/4 quasi-particle. So in the last 2 years, we have seen many measurements on the charge of these of anionic excitations for the 5-half state. Since this is not the major issue in my talk, I want to skip, but just would like to point out some of these stories get changed over time. So I don't really, at least let's say, well, they showed data consistent with the E/4 existence of the E/4 charge. So in the end, we want to look at the quasi-particle interferometer. This was proposed by of course many also a lot of some of them in the audience. And so I guess I probably don't need to elaborate. So this is the quantum Hall bar, and we have a few gates here that creates two quantum point contacts, and we might also need a side gate which can control either the area of the interference loop or maybe the number of quasi-particles in the ball. So this edge theory of 5-half is described by a chiral boson and a chiral Majorana fermion, we can write down the tunneling Hamiltonian as a tunneling of quasi-particle at quantum point contact 1 and a tunneling of quasi-particle at quantum point contact 2. So what's is most dramatic for this non-abelian quantum Hall state is the so-called odd-even effect. Basically, it depends on the number of quasi-particles in E/4 quasi-particles in the bulk, we may or may not see the oscillations. The easiest way of understanding it probably is these E/4 quasi-particles are Majorana fermions, so they should be accompanied with some branch cut. And if there's one such Majorana fermion in the bulk, and we should have a branch cut, suppose that it passed through this point-to-point contact. So then the quasi-particle moving in this direction does not feel the branch cut, but the one moves in this loop, in this path, feel the branch cut. So really the branch cut detects which path the quasi-particle is taking. So in the case of odd number of quasi-particles, E/4 quasi-particles, there's no interference pattern. Or effectively we can evaluate those polynomials. So as I mentioned, there are both E/4 and E/2 quasi-particles which are relevant to inter-edge tunneling. So which one is more important? If you read the literature more, you see dominantly discussion on E/4 quasi-particles. This is reasonable because if you really look at the tunneling amplitude, this one really dominates. So here I performed a microscopic calculation to show that. So I have a disk of 5/2 state, then I can create a quasi-particle at the center, and I can study the tunneling of this quasi-particle to the edge in a tunneling potential which breaks the rotational symmetry. So essentially I'm calculating this kind of overlap. I have E/4 quasi-particle tunnel to the edge, then I'm getting a Morley state. So this is my result for the tunneling amplitude of E/2 divided by the tunneling amplitude of E/4, and you can see that it is decreasing exponential as the system size is increasing. And just for comparison, I also show you the Laughlin case where I can either have E/4 quasi-particle at the center or two E/3 quasi-particles at the center. And you see a similar exponential decay. But in this case, actually, this one is irrelevant. So, but what I started here is really just the center-to-edge tunneling. To be more experimentally relevant, I should map that into edge-to-edge tunneling. So this can be done by inserting a lot of quasi-particle or flux tube at the center. So I did that, and actually my student did that. So then we can, with different number of quasi-poles, we can defines the distance between the two edges. So I plotted this ratio as a function of this distance for various number of electrons. So you can, so as I increase the number of quasi-hole in the center, I actually go from, for the largest system size, I go from this one to this, then to this, all the way to here. Apart, as you can see, apart from the case where I have very little or zero quasi-hole in the center, I do have curves falling on this universal curve. And my best fit gave me this exponential of minus 0.094. L squared, I think it should be D squared. Here I call it D. So D squared over L, the magnetic length squared. And I get from the fitting, it's 0.083. But one can do some very naive estimate based on the charge difference of the states before and after tunneling. And so this kind of tunneling amplitude is proportional to the charge square and the distance square. So from that argument, one expect in the Morley case, this ratio should be e to the minus 0.094. So here's the difference of the two, and here's the data. Yes.
Do you know why it seems to be curving up at on the outside?
As I said, this is the case with no quasi-hole in the center, so I really have a disk. So there it's, and as I move along this, so it goes from disk to annulus. I think it has something to do with this geometric factor. I'm not certain, but I think.
Is there any way of getting out the scaling exponents from this?
Probably no. I think this is just a feedback.
No. I guess you are changing the system size. For example, some finite size.
I was actually expecting some scaling, but in the end, I found everything can be, can be set. It's also in, I think, this, the paper by the five authors, starting with Hashara. They also have similar argument.
Because I guess it's not just the overlap; it's also that it's.
I think so. You see here also there's the deviation, so it's not exactly clear, why there's still separation, and but at least I can say the dominant factor is from the charge difference. So, and I should say that the tunneling amplitude I'm calculating here is the bare tunneling amplitude, which presumably will go in the RG flow, as both are relevant. But it is, probably true that the yield 4 will nevertheless dominate. Except for the case that we have two quantum point contacts. There's a twist which is related to decoherence, you already know. So this is about why we should see that difference, and I think you might have seen this already. So if we consider finite temperature effects, then these basically the propagator should pick up this temperature factor, and the amplitude of interference should be proportional to a few things. First, one should have this oscillation factor. This is the Aharonov-Bohm effect, and one should also get this from the tunneling amplitude. That's the tunneling of two quasi-particles at the two tunneling contact. And one also has this kind of form. This is from the coherent lens due to thermal smearing. And I just mentioned that the tunneling amplitude actually favors E/4 quasi-particles. But this one is written down here is inversely proportional to temperature, but it's also proportional to the scaling dimension divided by the edge mode velocity. Here for the charge and for the neutral one. The E/2, as I mentioned, it only contains the charge mode, so it does not have the neutral mode. So if the neutral velocity is very small, then this factor here would favor E/2 quasi-particles. So you do see here a competition between the E/2 quasi-particle and the E/4 quasi-particles. So I think I'm running out of time, so I don't need to go through the models again. So in a Maury case, we, again in microscopic calculation, we can identify these edge modes, but now we have both bosonic and fermionic ones. So you can see the identification. We have here 20 modes, 1, 1, 3, 5, 10. And the red ones are from exact diagonalization. The green ones are from these, these dispersions, and construct. We basically construct these modes from these 8 parameters. And although I should say that in this case I mixed the Coulomb interaction with the free body interaction. So to effectively separate my edge excitations and the bulk excitations, in the pure Coulomb case, I actually see mixture of edge excitations and the bulk excitations very hard to draw conclusions. So I normally do it with finite amount of three-body interaction that extrapolates everything down to the Coulomb limit. So here you already see that the difference between the bosonic mode and the fermionic mode, and this is what we call Bose-Fermi separation. You know, the two components actually can propagate with very different velocity.
So, question. You get those velocities from having Coulomb plus three body. So does this velocity of the neutral mode depend on how much three body you add in, or?
You'll see in the next, probably in the next one. So once, okay, so if you're not convinced with my argument that you know, these modes are these excitations are related to the fermionic excitations, and this one up there are related to bosonic excitations, I can give you a more explicit demonstration. So I can again trap quasi-particles in the bulk with a delta impurity potential. So as I tune the strength of this trapping potential, I see the ground state change from the Moore-Reed state to 1 quasi-host, 1 E/4 quasi-host state to 2 E/4 quasi-host state. And why it's E/4 you can see from the density difference. So if I look at the lowest energy excitations, so in a case with no quasi-hole, I have 0, 1, 1, 2. And with 1 E/4 quasi-hole, I have 1, 1, 2, 2. This change is due to the boundary condition for the Majorana fermions from antiperiodic to periodic. So if you now add 2 E/4 quasi-hole, or effectively 1 E/2 quasi-hole, then you see the spectrum change back to 0, 1, 1, 2. This actually is one way to demonstrate the non-Boolean statistics of the quasi-particle. As among other ways, for example, Steve did very recently this explicit grading of quasi-particles. So I think this is the nice, one of the nice part of the disk calculation, because we can exploit the connection between the bulk and the edge. So this is what you asked for. So these are examples of two different amounts of three-body interaction, and they have some similar spectrum, except the energy scale is different. So if I get the velocity from the energy difference here, then if I extrapolate, put them together as function of amount of three-body interaction I have, and they can be extrapolated nicely to some value in the Coulomb limit, which correspond to a charge velocity of 5 times 10 to the 6th centimeter per second, and neutral velocity of 4 times 10 to the 5th centimeter per second. So it's again a factor of roughly 10. Of course, this is one system, with one set of parameter and also finite system. I look at different sizes and different combining potential, and I see that roughly this ratio of charge velocity to neutral is always at least 6. So the question why neutral velocity is so small, at least in this chiral case, is not very clear. I don't think anyone has very good answers so far. So that's why back in 2007 we sort of wrote down in the long paper that embedded in the middle of the paper, in the interference experiment, it is possible that these E/4 quasi-holes is lost due to decoherence. We can still observe an interference pattern due to E/2 quasi-particles. And this is based on our our result in the earlier plot. So we ended up with an coherence length for E/4 quasi-particle at 10 millikelvin to be 4 micron. At the time we thought 4 micron is so small, so well, it probably, one may not be able to see anything like that. So, but Bob Willett did the measurement at 25 millikelvin, but he has a sample of size of 1 micron. So for this temperature, we estimate the decoherence length for E/4 is 1.5 micron, roughly the size of his sample, and for E/2 it's 5 micron. So his sample looks, I think you probably heard from Kirill already, so his sample looks like that. We have 2 quantum point contact. They're separated by a length scale roughly of 1 micron. So he saw both oscillations more consistent with E/4 period, as well as the oscillations more consistent with E/2. And in the Fourier spectrum analysis, he found peaks in both E/4 and E/2. So that really confirmed our prediction. So in one case, he increases the temperature from 30 millikelvin to 150 millikelvin. So we see these E/4 oscillations give way to E/2 oscillations, and in general, he had this kind of picture at very low temperature, we see both E/4 and E/2. Then at intermediate temperature, we see only E/2, and at even higher temperature, we see nothing. So we repeated our calculation now with including a lot of the factors like confining potential and the finite size scaling, and we ended up with a phase diagram like this. And according to our current understanding, that below certain temperature we should see both E/4 and E/2, and then E/2 in the middle, and above certain temperature, which is actually, you can see, not very much different from what Willett saw in the experiment. We have a coherent case. So I just want to say that these estimates on the neutral velocity, of course, we did what we could to do, best. But there's other effect we haven't really included. For example, there are things that we know which may have a minor effect. For instance, the layer thickness. But there are cases, we really want to consider but couldn't. Is the fact that we are only considering a system of u = 1/2, but with the appropriate Coulomb interaction parameter in the first lambda level. So there are 2 additional edges, and they can also screen the confining potentials to some extent. So maybe this nu = 5/2, nu = 1/2 edge is better protected, or maybe it, so that it feels very little edge confining potential, so its velocity can be even smaller. And these are things that we don't know from this microscopic calculation. What we can say here is, it looks like this E/2, the decoherence temperature for E/2 quasi-particle is less dependent on the confining potential. And the E/4 has a more stronger dependence on the E/4, on the confining potential. So if we really want to see the E/4, presumably in the non-linear statistics, one should try to maybe tune the confining potential a little bit to enhance the signal, and this is just a comment. And but on the other hand, this might be opposite. There might be an opposite trend for the anti-Feppian state, because there we really have a whole droplet of the Moride state. So with that, I'd like to conclude. So I told you that that this geometry allows quantitative calculation on edge physics, which reveals the bulk topological order. Charge velocity is dominated by Coulomb energy scale. Neutral velocity is generically much smaller, although in some cases we cannot tell. Non-abelian quasiparticles with the smallest charge are the most relevant in inter-edge tunneling, but the less relevant abelian quasiparticles fused from the non-abelian ones have larger coherence, length, and temperature. The competition of the two quasiparticles can lead to observable signature in interference experiment. I also expect that, if this is correct, we should also see it in the telegraph noise measurement. So I listed some of the reference related to the 25-half case. There are more on the archive, which you can find out. So thank you very much for your attention.
Other questions, comments?
In your part on the edge reconstruction, you discussed it in terms of the Chamonix picture where the part breaks off and you get additional edges. But at least at nu equals 1, there is numerical evidence that you have another reconstruction happening before, more softer, either a charge density wave condensing or a spin density wave. Do you see any signs?
Well, in the, I probably mentioned by passing, but not as elaborate. I do see, if I increase D further, I do see a well-defined edge droplet, then followed by some bulk. But again, if you really count the number of electrons, the largest system I can do roughly is 10 electrons. And the edge might have 6 electrons, and the bulk is just 4. How do you call them 4? An incompressible liquid. So I do see the tendency, but I wouldn't say that I have very solid evidence for that.
Questions? Okay, let's end this.
Tomorrow morning, first thing in the morning. Sorry, I missed you. Is it possible that I